Okay, so chapter 8, chemical bonding. We learn here how everything is connected. And the first one is about ionic bonding. Now, ionic bonding, usually you have a metal and no metal, right? So in periodic table, have the blue. All the blues here, the guys in blue, are the metals. In yellow, we have the nonmetals, and in green, the metalloid. So you learned in the previous chapters, right? The previous chapter that metalloids, they have properties of metal and nonmetal. So the metalloids you may have ionic or covalent bonds too. But for now, let's focus only in the metals and nonmetals. So in ionic bonding, you have a metal, right? The metals will be losing electrons, so will be positive. And the non-metals will be gaining electrons, so will be positive. So that it means in ionic bonding, the whole of electrons in ionic bonding. One is losing, one is losing, another is gaining electrons, right? So have the exchange of electrons, right? Electrons here. Okay, so the first example you have is sodium chloride. And let's see here, why sodium shows just one dot and chlorine is showing here 7 dots? The dots here, these dots mean valence electrons. Valence electrons are the electrons the outermost shell. For example, how do you know that sodium has one? Okay, so we have two ways, right? So the main groups, like for example, group 1, everyone here, all atoms in group 1, they have one valence electron. Group 2, 2A here, 2A, 2 valence electrons. Then we skip the transition metals here, right? And then 3A, group 3A, 3 valence electrons. Group 4, group 4A here. For A, 4 valence electrons, then 5. 5 is valence electrons, 6 valence electrons, 7A. The halogen, 7 valence electrons. The noble gas should be right here, but something happened that the periodic table here is not showing, but right, the noble gases right here, the last column, you have the noble gases, 8 valence electrons usually, with exception of helium. That's only 2 valence electrons, but all another ones here in the noble gases, they have 8 valence electrons. Okay. Right, so let's show here. Another way is writing the electronic configuration for sodium. How many electrons do you have in sodium? Total 11, right? Here, atomic number 11. Okay, so let's write it here. The electronic configuration, 1s2, 2s2, 2p6, right? 2 plus 2, 4 plus 6, 10, then 3s1, right? 1. How many valence electrons you have in sodium? The valence electrons are the electrons at the outermost shell. In that case, you have 1s2 here, just 2 electrons. Then the energy level 2 have 2 plus 6, 8 valence, 8 electrons, and right here, 3s1. In the case here, 3 is the highest energy level, have just 1. So that's why here for sodium, just 1 dot, because the sodium atom has just 1 valence electrons, right? That means the electrons, they are in the outermost shell. The outermost shell. In that case, chlorine, right? Chlorine here, oops, 17 electrons. So chlorine, 17. So 1 S2, 2 S2, right? 2p6, 3 S2. So write the electron configuration, you write until you get the number that you want. 17, right now I have 2 plus 2, 4, 16, then 12, then 3p, 5, right? So now, how many valence electrons you have in chlorine? So I'm going to count how many electrons you have in the outermost shelf. That means the highest energy level. That is here, all the electrons, they are in the number 3, energy level 3, you count to be the highest outermost shelf. So 2 plus 5 is 7 valence electrons. That's why here chlorine has 7 dots, right? 7 dots, 7 valence electrons, 1 dot, 1 valence electrons. So, but when you combine sodium with chlorine, when you combine here, right? Sodium is donating 1 electron to chlorine. I've seen here. But why chlorine is donating? Now, everything is about stability. The atoms will be losing or gaining electrons to achieve stability. What stability? Stability is we're going to be getting the highest energy level be the full orbitals. Or the electrons having full orbitals. So, for example, 3s1, right? There's 1 electron. Now we'll be going to chlorine, right? So don't have the 3s anymore. You have now 3p6. Right? Now let's count how many valence electrons you have in sodium now. Before was 1, but now, right now, you have 2 plus 6, 8, right? 8 valence electrons. The same thing for chlorine. Chlorine before had 7 valence electron, now gained 1 valence electron, so chlorine now also will have 8 valence electrons, right? So the atoms, they are losing or gaining electrons to achieve the octet rule here. That means 8 valence electrons, octet rule. They want to be stable, happy when they have 8 valence electrons. Yes, you have some exception like hydrogen, it will be happy, stable only with 2 electrons. The same thing for helium that has already 2 electrons, right? So another way here, all elements group 1A, you have 1 valence electron. This 2A here, group 2, 2 valence electrons. Then we skip these, the transition metals, and then continue here. Group 3A, 3 valence electrons, 4A, 4 valence electrons, 5, 6, 7, 8, 8 valence electrons. So noble gases, they have 8 valence electrons, with exception of helium. Helium has only 2 valence electrons. In other words, the atoms, they are losing or gaining electrons to achieve noble gas configuration, right? For example, here, sodium initially was what? 11. Now, how many electrons you have in sodium right now after lost one? Right? Now the last one will be positive, right? Now you have 2 plus 2, 4 plus 6, 10. The noble gas that it has 10 electrons is neon, right? And now chlorine, that was initially 17. Now when gain 1 will be minus here. So now that it has 18. Which noble gas has 18 electrons, right? So it's argon, and it has 18 electrons. So the atoms, they are losing or gaining electrons to achieve noble gas electron configuration, okay? Here, ionic bonding, the electrons have exchanging. One is gaining, another is losing electrons. The next topic, thing about ionic compounds, is properties of ionic compounds. All right. So the metals, right, make ionic bondings. They have the ionic compounds. They have high melting point. High melt point. They have the ionic compounds that have a high boiling point, right? They are what? Solid. They're solid, right? They're crystals and solid crystals, right? And what else? They usually dissolve in water. Usually, the ionic compounds usually dissolve in water. And then when they are dissolved in water, they can conduct electricity. The ionic compounds, when dissolved in water, they conduct electricity. When is dissolved in water. So why? When they're dissolved in water, the sodium, like for them, sodium chloride, right? It's right it's like there's a solid. There is no charge here when it's solid, right? No. But when they go in water, they'll be dissociate into ions. So that it means the water, it will have a positive and negative charge in the water. Ions, positive and negative ions. So we have in this, when water here, will conduct electricity, because when conduct electricity, there will be ions, right? Okay. The next is lattice energy. Lattice energy and energy required to completely separate 1 mole of a solid ionic compound into a gas atom, ions. So sodium chloride here, to break this, to be converted from solid to gas, it needs 788 kilojoules per mole of energy, right? There's a lot of energy here. Wow. And by the way, and when it's positive, means absorbing energy, right? Will be endothermic process. That we saw in previous chapter 5, right? Yeah. Endothermic process, the enthalpy will be positive here. And what may affect the energy? The lattice energy here. Size and charge. So let's look to the try to understand this graphs here. So in this direction says increasing radius here, radius. Increase the cation radius. When the size is increasing, right? The cation is increasing here. The energy is decreasing. Right? Okay, so when the size, right, like decreases, in that case here, when the size increases here, the lattice energy decreases. Why? So when the atoms, they are smaller here, right? The bonds, the cations and ions, they are smaller, they'll have more attraction, like the higher effective nuclear charge. So it'll be harder to break these bonds here when they are smaller, right? That's why when when they increases, you need less energy. When they are smaller, you need more energy. The same thing for anions here. Okay. Oh, yeah, this one, yeah. Right. In chapter 7, that was about periodicity, right? You saw that usually almost everything from bottom to top increases. And from left, it's blurry a little bit. Okay, now it's okay. When from left to right and from bottom to top, almost everything increases, except everything related to size. So from bottom to top, the size of the atoms, like decreasing size, the size decreases here. And from left to right, also the atom here, the size also decrease. All right. So now it's Lewis dot structure. We're going to use the dots to represent valence electron that was talked in the previous page, right? For example, group 1A, all the atoms group 1A, they have one dot. That means one valence electrons. 2A, two dots, just here. So two valence electrons. Then we skip the transition metal, right? And then go back here. 3A, three valence electrons. 4A, four dots, so four valence electrons. 5, 6, 7, 8. Each dot means valence the electron, right? Okay, so this practice problem here. This structure for format for ionic compound. Binary ionic compounds here. You have sodium chloride. First thing was the name here, so sodium chloride, right? Sodium chloride. And then, oops, sorry. And then this question asks you to show the Lewis structure. So Lewis structure are going to show how the atoms, like the structure, how the atoms are bonded, right? So, okay, sodium chloride, you know that sodium has initially one dot, right? We saw that in the previous, and chlorine, 7 dots because it has 7 valence electrons in the group 7A. Then sodium donate 1 electron to chlorine here, right? When you have this, sodium is now positive and the chlorine is negative, right? So how gonna be the Lewis structure for sodium chloride? Will be like sodium in brackets with means the positive here because it lost 1 electron, right? And then the chlorine, you have now 80 dots inside the brackets with the minus, meaning that it gained one valence electrons here, one electron. So binary compound, because it has only two atoms here, and it means he also should be binary ion compound, binary. And you have aluminum and oxygen here. So aluminum is the metal, right? To be losing electrons. And the oxygen is the non-metal, so it'll be gaining electrons. Sodium chloride, right? Already saw that sodium is the metal and chlorine is the non-metal. Okay, so now you have two aluminums, right? And three oxygen. How we're gonna do this? First, let's answer the name. So in ionic compounds, you just name the first element as it is, right? The second, we're gonna change the suffix to "ide." So here, aluminum oxide, aluminum oxide, right? So, and then you have these three aluminums. Oh, sorry, two aluminums here, aluminum, and three oxygen here. So each aluminum, right, group 3A, so three valence electrons. Let's go here, three dots, one for three dots here. And oxygen group 6A, so six, right? 6A, six valence electrons. So 1, 2, 3, 4, 5, 6. Actually, it's like this. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. Like it's so close to one another here that it was hard to show the dots. Okay, so you have this aluminum here, donate one, each aluminum here. You donate two electrons to each oxygen because oxygen has already six, right? Six valence electrons. How many electrons it needs to get eight? Plus two electrons, right? So you have eight valence electrons. So aluminum here, donate one. Now oxygen has seven. Another one. Okay, now this oxygen here has eight valence electron, right? Let's go to the next one. I think this, but aluminum here still has a left dot, right? So this will be donated to the second oxygen. Right now it will be this oxygen. Now that it had six, now we have seven. That means this second oxygen still needs one more electron. So let's get here. Okay, nice. And it means now this oxygen here had six, gaining two electrons. So gonna be eight valence electrons, right? And aluminum, that was the last aluminum here that still did not donate two, has still two left valence electrons. We donate one, each one. We still donate now to the last oxygen. So all the oxygen now has eight valence electrons, right? So how will be the Lewis structure here? So how many aluminums you have here? Two. So let's write number two here. And then the brackets, aluminum right inside the brackets, right? Aluminum. How many electrons had? Initially three, and each aluminum lost three electrons. So 3 plus. And about oxygen, oxygen in the brackets, right? So each oxygen now has 8 dots. That means 80 valence electrons. And each oxygen gained 2 electrons. So here, the Lewis structure for aluminum oxide is this one here, right? Okay. And let's go to the next topic here. Oh, no, here. So let's go. Next stop is covalent compounds. In a covalent compound, you is between a non-metal and non-metal. Okay, so now they have these metals. They both want to gain electrons. How gonna solve this problem here? Right? In ionic bond, one was metal, right? And another was non-metal. The metals want to lose, they're gonna be donated to the metals, right? But in the non-metals both want to gain. So how gonna solve this problem here? The both want to gain, that means they'll be sharing electrons. Sharing electrons. So nobody's gonna lose. No metals will not lose electrons. They're gonna be sharing electrons. Usually between no metals. So electrostatic interactions in a covalent bonding, you have attraction between electrons in nuclei, right? The nucleus of each electron, or between each atom here, and repulsions between electrons and repulsion between nuclei. So the electrons repel each other, and the nuclei will also repel each other here. And the nuclei and the electrons, they attract each other, right? When you have it, it's like here, the nuclei, they are positive, electrons, they are negative. Right. Now, properties of covalent bond compounds. So you saw that in ionic bonds, you have a high melting point and a high boiling point, right? And covalent is the opposite. Covalent, you have low boiling point and low melting point. Covalent compounds, they are the opposite. They have a poor electroconductivity or electrical conductivity. And they usually, so yeah, ionic compounds, they usually dissolved in water, right? But for covalent compounds, usually, oh, I messed up here, sorry. Usually do not dissolve in water. In water. But in organic compounds. Now, the little structure for covalent compounds here, right? So let's do here. We have these steps, 5 steps to draw the little structure of covalent compounds or molecular compounds. First, sum the valence electrons from all atoms. Take into account the overall charge. Okay, so let's use as example here. CH4. First is the name. What's the name for CH4? So we have here hydrocarbon. So this in chapter 2. And the hydrocarbons, they are organic compound. In organic compounds, they have a different way to name the compounds, right? So then there's here meth, just one carbon, and all here you have a single bond, so methane. If you had two carbons, for example, and you would have six hydrogen, it would be ethane, right? But here just one carbon, so methane. So okay, some the valence electrons for all atoms take into account the overall charge. Are you seeing any overall charge here? No, right? So no extra electrons or no subtracting electrons here. Now let's count the valence electrons CH4. Carbon, group 4A. So carbon has 4 valence electrons, right? And about hydrogen, right? How many hydrogens you have here? So 4 hydrogens, right? And each hydrogen is group 1A, right? So 1 valence electron. So you have here total here, right? 4 from carbon and 4 from hydrogen. Each hydrogen is 1. So stage 4 has 8 valence electrons. Right. So after you count the overall the valence electrons here, write the symbols of the atoms, show which atoms are attached to which, and connect them with a single bond. Each line represents 2 electrons. Okay. So let's do here. Carbon, the center, hydrogen, 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 and hydrogen, right? Then you write the symbols, connect with a line. Okay, let's connect with a line here. So each line represents 2 electrons. So let's count how many electrons we have here. 2, right? Plus 2, plus 2, plus 2. So CH4 with the bonds has already 8 valence electrons. That means right now, CH4 is done this way. They don't need to do anything because only with the lines, you already can count 7, 8 valence electrons. So use structure for CH4 is just this. And we are done here for CH4. Chlorine. Chlorine here, right? Cl2. How many valence electrons have in each chlorine? The chlorine is a group 7A periodic table, right? Chlorine here, 7A. So that means 7. Each chlorine has 7 valence electrons. And how many chlorines you have right here? 2, so 7 times 2. So the CO2 molecule has 14 valence electrons, right? Okay, we counted right now. Let's write the symbols. Okay, chlorine with chlorine. Then let's connect them with single bond. Okay, I did connect. Now let's complete the octet. Let's write the dots here. Okay, what you have here? Each line, 2 electrons, right? So 14 minus 2, 12. So I still need to place 12 electrons around these chlorines here. Okay, so let's use the dots, right? So 1, 2, 3, 4, 5, 6, 7, 8. So 8 for this one. And for the second, 12, right? So let's draw 6 dots in each chlorine. So now each chlorine has 6 dots. And in one line, each line counts 2 electrons. That means each chlorine is happy, right? With 8 valence electrons. So what's the Lewis structure for chlorine? Will be chlorine, bonded chlorine, with each chlorine has 6 dots. So the Lewis structure will be using the dots to represent the lone electrons, that means not bonded, and the line to represent the electrons that are sharing electrons here, the bonds, the lines. Okay, next one is ammonia. Ammonia here, right? Ammonia, how many valence electrons do you have in ammonia? Nitrogen, 5A, right? And so here, there's 15 actually here. Let's express actually to 5A. And all the 5A here, they have 5 valence electrons. So nitrogen, 5 valence electrons, right? Plus each hydrogen has 1 electrons. How many hydrogens do I have here? 3, right? Sorry. Times 3, right? That means the energy 3 has total 8 valence electrons. Now let's do this next step, right? Write the symbols, all right? And here, and here, here, and here. Then connect the line. 1, 2, 3. Now let's complete the octet. Let's complete to have 80 electrons. Hydrogen is an exception. Hydrogen is happy only with 2 valence electrons, right? That means hydrogen only needs to make 1 bond, and there is no electron around, no dot around. So hydrogen, 2 electrons, good. This hydrogen here, 2 electrons. This hydrogen here also 2 electrons, right? So all hydrogen here is already 2 valence electrons, and they are all happy over here, right? For hydrogen, happy with 2 electrons. It means stable. But now let's count here, right? How many electrons do we have here in the bonds? Each bond 2 electrons. 1, 2, 3, 4, 5, 6. Okay, 8 minus 6. So we still need to place 2 electrons. Where we are going to place here? In the atom, the central atom, right? Because all the hydrogen here is already all complete. So let's add 2 dots in the nitrogen, the central atom, because the hydrogen is already stable with 2 electrons. There is no dot to add here. So now, how many valence electrons you have in nitrogen right now? 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen now has 8 valence electrons. That is here, right? Complete the octet around the atom bonded to the central atom here. So the Lewis structure for NH3 is right here. And like this, the Lewis structure here. All right. Okay, but sometimes it's not only single bonds. Carbon dioxide. What's the formula for carbon dioxide? C, carbon dioxide, that means 2 oxygens, right? What's the Lewis structure for carbon dioxide? Let's follow the same molecular compound, right? That's covalent, means covalent. First, sum the valence electrons. for all atoms. Carbon is what? Carbon has a 4A, so 4 valence electrons, right? Plus oxygen 6A, so 6 valence electrons to oxygen. And you have 2, so 2 times, right? So how many valence electrons you have in CO2 here? Carbon dioxide. 6 times 2, 12 plus 4, so 16 valence electrons, right? Okay. Now let's draw here. Let's connect the symbol. The carbon is the central atom, then 1 oxygen in each side, right? Next step is connect the atoms here. Now let's count the valence electrons. Okay, so this molecule should have 16, right? But now how many you have? 1, 2, 3, 4. Okay, 16 minus 4, right? Minus the lines here. So gonna be 12. Okay, 12 valence electrons. So let's place 6 in each oxygen. 6 valence electrons, then 6 valence electrons. Okay, now let's count how many valence electrons you have for everyone. So everyone in here should have 8 valence electrons, right? Let's count. Oxygen, 1, 2, right? Each line counts 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8 for oxygen. Okay, in this carbon, 1, 2, 3, 4, 5, 6, 7, 8. Okay, also 2, 6, 8 electrons, right? All right, and about carbon, 1, 2, 3, 4. Okay, so carbon does not have 8 valence electrons here. So it's not right yet. So what we're gonna do when you already used all valence electrons, but one of the atoms does not have 8 valence electrons, you are going to make double or triple bond as needed. So let's get these electrons here, right? These 2 electrons here to be sharing, be converted to shared electrons between oxygen and carbon. So here, oxygen still has 8 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. And about right now, does carbon have 8 valence electrons already? So 1, 2, 3, 4, 5, 6. The answer is no. So oxygen has still the 8 valence electron here, but not carbon. I'll follow the same thing. I'm gonna use these 2 electrons for oxygen. They're gonna be converted to a bond to be sharing bonding between oxygen and carbon. So how many valence electrons you have in oxygen? 1, 2, 3, 4, 5, 6, 7, 8. The same thing here, 8. And about carbon in the center. 1, 2, 3, 4, 5, 6, 7, 8. So now, good, right? So now everyone has 8 valence electrons. All right.